We're going to focus on water and, of course, include chemistry in its application to water. Module 5.1 discusses water and its chemical properties. So we know water is ubiquitous in nature. It's all around us. It's everywhere. It covers, 70% of the Earth's surface. It's in us as mammals. It's really essential for life, indispensable. And out of all the water on our planet, only about 2.5% of it we can drink. So it is a limited resource. As just mentioned, fresh water, it's about 3% found. That means about 97% of it is salt water. But within the fresh water, most of it is in glaciers. It can be also found in lakes, underground as well, and has to be pumped up in wells. But most of it is in glaciers. And to compound the fact that we only have 3% fresh water, a lot of it that we use is actually, we wasted about 3/4. I don't know if you know, the water in New York we get actually comes from upstate. It comes down into New York City. Some sources of water pollution include mines that are no longer running, some landfills, chemicals that we pour down the drain, chemicals in the lab that we should not be pouring down. We should be disposing it properly. So there are many sources of water pollution as well. A little bit of chemistry. At 1 atmosphere, which is the pressure around sea level, and at 25 degrees, we know water, H2O, is in the presence in its liquid form. Other things that are important to us at 25 degrees Celsius and 1 atmosphere, we know oxygen is in the gas form, not liquid or solid at those conditions. Nitrogen gas as well. We know that water boils at 100 degrees Celsius, that's at sea level. If you go up in altitude, that boiling point decreases because the air pressure is less. And we know that water, H2O, has similar properties to H2S. And I think I briefly touched upon this. It's because oxygen and sulfur are in the same column or same group of the periodic table, so they share similar properties. You've experienced that if you put water in a cup and you put it in the freezer, over time that cup could actually crack, and that's because water actually expands. You might think the opposite, because when you go from a liquid to a solid, the molecules come closer together. But for water, it's very unique that when water freezes, it actually expands, and that's due to hydrogen bonding, which we'll talk about in a second. Recall that H2O has a bent shape because of these lone pairs. So before we get to that, electronegativity is a way to measure the attraction of an atom for electrons in a chemical bond. So if we look at the example of water, H2O, we know that the electronegativity of H, so you don't have to memorize this will be given to you, is 2.1, and that of oxygen is 3.5. The 3.5 has a stronger electronegativity. That means the electrons that live in this bond will spend more time around oxygen. So that will give oxygen a partial negative charge. And because one is negative and the other one will, as a result, be more partially positive. And we saw this a little bit when we were talking about IR and radiation. IR radiation, how if you have a dipole moment, it can absorb some of the IR energy if we have this dipole moment. So if there is a dipole moment, we can call this a polar covalent bond. Recall polar means polar covalent. Covalent means that they're sharing electrons, and polar means simply that one end is more positive and the other end is more negative. And in our case, for water, water will be partially negative and hydrogen will be partially positive. The difference here between 3.5 and 2.1 is 1.4. Some things that are nonpolar are Cl2, O2, and you notice that they would have the same electronegativity values. So essentially the electronegativity difference between Cl and Cl is 0. So it's a nonpolar covalent bond. As we mentioned, water is a polar molecule. It has partial negative and partial positive. We also introduce hydrogen bonding, and hydrogen bonding entails hydrogen bonding to either the nitrogen, oxygen, or fluoride. So here's an example of a hydrogen bond. It's between molecules, so we call that intermolecular bonds, hydrogen bonding. So it's between molecules versus intra is within a bond. So this is a intramolecular bond, intramolecular bond. Covalent bonds are intramolecular, but hydrogen bonding is between molecules, hence intermolecular bonds. So we talked about earlier that physical changes involve going from one state to another. This is highly due to the hydrogen bonds and London dispersion forces. So if we have physical changes, for instance, water going to ice or water going to steam, we're breaking the intermolecular forces between water molecules. Versus chemical change, for instance, if we decide to break apart a water molecule, we're actually breaking a covalent bond. That would be a chemical change. And we say intramolecular forces are being changed. I mentioned earlier that ice, when ice is formed, it actually expands. And that's because the hydrogen bonding, this is due to hydrogen bonding, and it actually makes a lower density. When ice forms, it actually takes up more space. And because it takes up more space, the volume increases, but the mass stays the same, and therefore the density will be less for ice than water. That is why we observe ice floating on water. And that's very important because for marine life, for instance, if we did not have ice floating on water, that would interrupt our aquatic life quite a bit if we had water on top of ice. So water is more dense than ice, and that's due to hydrogen bonding, taking up more space when ice forms. And we'll stop there about water, and we'll talk a little bit more about acids and bases and solubility later on.